Hello everyone. Can you all see my screen?
Yes, sir.
Okay, so I guess we can start with the tutorial. This is tutorial number 10. In this one, we will look at some questions on linear phase systems and generalized linear phase systems, and also some other questions regarding frequency response. So, let me start with the first one. It says determine the group delay for omega between 0 to pi for each of the following sequences. And this is the sequence that has been given to us x1n, which is n minus 1 for n1 to 5, and 9 minus n for 5 to 9. So we have to find out the group delay. Okay, so let's look at this one first. So this is how the signal looks like when we plot it. So you can see that for n is equal to 5, let's say, the value will be n minus 1 or 4. And for 1 to 5, it is increasing. And for 5 to 9, it will be decreasing. And when we plot this, we get something like this. So the reason to plot this sequence is to see where it is symmetric, because we know by symmetry that it will be a linear phase. When the impulse response is symmetric, then the it is a linear phase system. Now, for linear phase systems, the general form is given by this. This is the Fourier transform, which is some magnitude h e raised to the power j omega e raised to the power minus j omega alpha. So you can see that the phase is minus omega alpha, and it is for minus pi to pi. And this is the argument or the phase, which is minus omega alpha. So it is a linear function of omega, right? And we can see that there is a symmetry about n is equal to 5. So that means that this alpha here is 5. So we can say that argument of this function is minus 5 omega. Now, simply we have to calculate the group delay, and we know that it is minus the derivative of the argument with respect to omega. So it's this function over here. So that clearly it's just equal to 5. So it was just this. So the group delay for this case is 5. We can do something like this only for the second case as well. So in the second case, we have x2n, which is this one. So again, in this case, we have not been given for what values of n, but we can plot and we will be able to find out symmetry. So clearly, when let's say if I put n equals to 0, I'll get 1 by 2 inverse, and this will be 1. So it will be around uh, 3, I guess. So sorry, it will be 3 by 2, 1 plus 1 by 2, it will be 3 by 2 at n is equal to 0, and so on. We can plot for all these values to see where it's symmetric about. So obviously this is also symmetric, because at 0 and 1 it is 3 by 2, then at minus 1 and 2 it is 3 by 4, and then minus 2 and 3 it will be 3 by 8. So when we plot this one as well, it is also symmetric, right? And um, since this is also symmetric, we know that it is also linear phase. So that makes calculating the group delay quite easy for us. We can just see in this case that the symmetry is about this point, somewhere between 0 and 1. So it's 1 by 2, and this part is symmetric to this part. And that is why we can say that alpha, or yeah, alpha in this case is 1 by 2. When we calculate the argument, that is minus omega alpha, it becomes minus omega by 2, and then we can calculate the group delay simply by minus the derivative of the the argument, and it will be 1 by 2. Yeah. So that was the first question. It was quite straightforward. We just had to calculate the group delay. And considering the fact that it was a linear phase system, it became quite easy. Let's look at the second question. We have been given some uh, zero plots, or we can call it the pole zero plots, where the system does not have any poles, and it's just the zero plots. And we have for corresponding to different system functions. So each of them is corresponding to some hz. And for these plot, we have to uh, state whether it could be a generalized linear phase system which can be implemented by a linear constant coefficient difference equation with real coefficients. So that means that hz will also be real. So that is what we have to determine, whether or not this system function could be a generalized linear phase system. Okay. So if we look at the first case, there are two complex conjugate zeros inside the unit circle and two that are lying outside. So let's reason on whether or not this will be a generalized linear phase system. So part two, it's this one. So the first thing that we observe in the first case is that the zeros come in a set of four. There are four zeros. There is a zero, its conjugate, and two conjugate reciprocals. Because you see that in this case, if we take the conjugate reciprocal corresponding to this, I will get this one. And similarly for its conjugate, the conjugate reciprocal will be this one. So if I have to write it down, I can write it down like this. This is the first zero, and this is its corresponding conjugate. And then the other one is its inverse, the one which was lying outside. And corresponding to that, the one which was lying outside, its conjugate. So it has an overall this form. So from this, we can tell that this is the general form of a type 1 FIR linear phase system, and therefore this can be this is a linear phase system from this arrangement. And obviously it is a finite impulse response because there are no poles. And so we can implement this using a linear constant coefficient difference equation, or LCCDE as the abbreviation. So that is how this we solve this first one. So now let us look at the second case. So for this one, I'll ask you all if you think this is a generalized linear phase system or not. So what do you think about this one? Any ideas?
I guess it is
It is. Why do you think it is a linear phase system?
because this can be also written as like polynomial of conjugate roots. Sorry, reciprocal roots. But they can
Yeah,
no.
you're right.
No,
But yeah,
the conjugate are not present, so I guess this will not be.
exactly. Yes, correct. So you're right that the reciprocals are present, but they are not in conjugate. So whatever the polynomial we'll get will not be real. So that is why this is not a linear phase system. And let us look at what it says. So it says that the linear constant coefficient difference equation has real coefficients. Therefore, its poles and zeros must come in conjugate pairs. So this cannot be a generalized linear phase system which can be implemented by linear constant coefficient difference equation for this reason only. And finally, we have a case where we have only real zeros. So there are three zeros, Clearly this one has a reciprocal here, and we have 1 0 here. So if we notice this case, so in this case, first of all, the first thing we need to notice that the number of zeros are 3, which is odd. And there is also, so if we recall from the symmetric uh, FIR linear phase systems, we say that if M is odd, then in that case, it must necessarily have a 0 at Z is equal to minus 1. So this is for the case of type 1 or type 2. And since M is odd, that tells us that it is type 2 FIR linear phase system, right? Because for type 2 and type 4 FIR systems, the value of M was odd. And since this also satisfies the fact that having M is odd gives us a 0 at Z is equal to minus 1, we know for sure that this is type 2 FIR linear phase system. And so if it is one of the types of the linear phase systems, which means that we can represent it through a linear constant coefficient difference equation. So this one is also a linear constant coefficient difference equation. So with this is the end of question number 2. Any doubt so far?
No, sir.
Okay, let's move on to the next question. So this question says that we have been given this time some pole zero plots. So there are poles as well. Together with the specification of the ROC, so we have been given some region of convergence as well. And this describes the overall system function. So each of these figure is one system function. It corresponds to one system function. In each case, determine whether any of the following statements are true and justify your answer with a brief statement. Okay, so we have to determine two things. The first one is that the system is a zero phase or a generalized linear phase system. And the second one is that it has a stable inverse. So we have to determine these two things for each of these cases. So there are 4 cases. Okay, so let's start with the first one. We see that there is one pole at Z is equal to 1 by 2 and 2. So one pair of complex conjugate poles, and there is a 0 at mod Z is equal to 0 at the center of the unit circle. And so let's look at how we will justify these two statements, whether it is a zero phase or generalized linear phase system, and whether or not its inverse is stable. Okay, so this is question number 3. So to tell whether it's a zero phase sequence, so recall that for zero phase sequences, all the poles and zeros are in conjugate reciprocal pairs. Okay, and the second thing is that for generalized linear phase sequence, it is composed of the zero phase sequence plus there is some time shift element, and corresponding to that time shift element, we see that in the pole zero plot there are additional poles or zeros which are at 0, 1, -1 or infinity. So we will use these two facts in order to distinguish whether it's a zero phase sequence, a generalized linear phase sequence, or neither of them. And we know how we also have to prove the stability of the inverse, and we know that for a stable system, the region of convergence must include the unit circle. So for the first case, we saw that there are so it says that the poles are not in conjugate reciprocal pairs because we had a complex conjugate pair, but corresponding to that, there was no reciprocal pair, right? So we can tell that it's not a zero or generalized linear phase system because it violates the condition for a zero phase sequence, which is that should be complex conjugate reciprocal pairs, and that's why it cannot be generalized linear phase as well, because generalized linear phase means that the condition of zero phase sequence must also be satisfied. So the first one is out of the way, it is neither one of them. Now we can calculate its HIZ, the inverse. So remember, when we compute the inverse, what happens is that the zeros will become the poles and the poles will become the zeros, right? So that means that since uh, the inverse will have a pole at z is equal to 0 or z is equal to infinity, right? So because you see that in this diagram we have a 0 at z is equal to 0, so corresponding to that we can have a pole at z is equal to 0. So yeah, so when we and also there can be a pole at z is equal to infinity corresponding to the difference in the number of poles and zeros. Remember what we do, we try to balance the number of poles and zeros by putting poles and zeros at infinity or zeros. So therefore that's why it says that perhaps it can have z at z is equal to infinity as one of the poles as well. And now we try to make the region of convergence. So for the region of convergence will be uh, there is a pole at z is equal to 0. We just select 0 to infinity, and that way we for the inverse, right? And when we do this, we can include, so this is outside 0, which is one of the poles, and it will be stable because it includes the unit circle as well. So we can have this as one of the valid ROCs, and for this one it is stable. And if this contains infinity as well, so it will also be causal. Or I mean, if there is no pole at z is equal to infinity, then it will be causal, right? Because then in that case we can say that it's outside the outermost pole. Okay. uh, so that is what we can tell about the inverse, that it will be stable. Let's look at the second part. In the second part we have something like this. So we have zeros now, one of them lying here and one complex conjugate. So first thing is clear that when we take its inverse, all the poles will lie inside the unit circle because they will correspond to the location of the zeros. And there is one pole at 0 and one is at 3 by 2. And it's given that the region of convergence is greater than 3 by 2. So it's outside the outermost pole. So remember that since we are given an ROC, that means that whenever we calculate the inverse, we must have the ROC of the inverse overlapping the ROC of HZ. Okay, so in this case also we can see that we do not have zeros in the complex reciprocal pairs. So obviously this is also not a zero phase or a generalized linear phase system. So that's what this says, that poles are not in conjugate reciprocal pairs, so it is not a zero or generalized linear phase system. The second thing is that poles of the inverse will lie inside the unit circle. Now when we have to compute the region of convergence, we take it in a way that it also contains it also matches the ROC of HZ. So for HZ, the ROC was mod Z greater than 3 by 2. For the inverse, we have taken mod Z greater than 2 by 3, right? Because 2 by 3, if you look at it, is this point. So we have taken it outside the outermost pole, and that is why we will have HIZ, which is stable because it contains the ROC. Sorry, it contains the unit circle. The ROC contains the unit circle, that is why it is stable. And it is causal because we have taken it outside the outermost pole. So before we go on to the next two parts, are there any doubts so far?
No, sir.
Okay, let me go to the third part. And in this part, we have an FIR system because there are only zeros. We see that the zeros are present in complex conjugate pairs as well as their reciprocals. So the reciprocal of this pair is these two outside. So clearly, this is a zero phase system. So for the third case, it says that zeros are in complex conjugate reciprocal pair, and there are no zeros or no zeros at z is equal to 0, -1, 1, or infinity. That's why it's not a generalized phase system, it's just a zero phase system. So that part is clear. Now looking at the poles of the inverse, first of all, uh, so all the zeros will become the poles for HIZ, and they are lying both inside and outside the unit circle. In that case, we can select the region of convergence to be the ring between these poles. So this ring will be such that since two complex conjugate pair will be inside, or sorry, one complex conjugate pair is inside and one complex conjugate pair of poles is outside. So the ROC contains a ring that includes the unit circle, and that is why it is stable. But it is non-causal because we it is not outside the outermost pole. So that is what we can say about HIZ. It will be stable but non-causal. Finally, the last part. So in this part, we have complex conjugate pairs of zeros, and all of them lie on the unit circle. So clearly, for the inverse, the poles will lie on the unit circle as well. And secondly, we see that we have zeros in reciprocal pairs. So for the D part, it says that the zeros occur in conjugate reciprocal pairs, and that is why it is a zero phase system, just like the previous case. And talking about the poles of HIZ, all of them lie on the unit circle. So whenever we make the region of convergence, it won't contain the unit circle because it will be from Z greater than 1 to infinity. That's why it does not contain a unit circle, and that is why the inverse is not stable. So this was question number 3. Based upon these the definitions of zero phase and generalized linear phase systems, we have determined, we have commented on these characteristics.
Sir, last two
Okay,
parts are
this is question
general
number
phase
4.
systems
This
as
is the
well, right?
last question. No, actually, for it to be a general phase system, there must be zeros at -1, which is this point, 1 or 0, or at infinity.
Okay. Okay.
I mean, you can, yeah, uh, because this, just like we saw in that, so these are the conditions on which we are characterizing whether it is a zero phase sequence or a generalized linear phase sequence. So for a generalized linear phase sequence, there must be, in addition to zero phase, these additional poles or zeros. Otherwise, it's just zero phase sequence.
Okay, sir.
And these are different. It is not that this is some special case. Zero phase sequence is not a special case of generalized linear phase sequence, because here, if we look at the phase contribution, it is 0, and for generalized linear phase sequence, the phase is some affine function of omega. We have something like minus omega alpha plus some other term. So that's why. They are different. Okay, so for the last question, we have been given so it says that a specific minimum phase system has system function h min z such that h min z times h apz, which is an all pass system function, is equal to h lin z, which is a causal generalized linear phase system. So the first question says, what does this information tell you about the poles and zeros of h min z? Okay, so basically we have two system functions. One is corresponding to minimum phase systems, which means that all its poles and zeros are inside the unit circle. And one is the all pass, which means that its poles and zeros are reciprocal pairs of each other. And when we take the product, it is giving us a causal generalized linear phase system. So it's asking us what can we say about this h min z. Okay, so well, in this case, the first thing is we have to understand that for minimum phase systems, all poles and zeros are inside unit circle. And for all pass systems, we know that pole zero pairs are at conjugate reciprocal pairs. Now, for the generalized linear phase systems, we have the pole and zero pairs in the conjugate reciprocal pairs, as well as z is equal to 0, 1, -1, and infinity. So we can also have poles and zeros at these positions. So basically, there can be two cases of how the minimum phase system is. So one possibility could be that within that unit circle, we have a real pole. And the other possibility could be that we have a complex conjugate pair of poles. In either of the cases, because we also have an all pass system, so for the generalized linear phase system, if there is a pole inside, there will also be its reciprocal outside. Similarly, if we have a pair like this, then there will be corresponding poles outside, which is the reciprocal conjugate pair. So these are the two possible cases which can happen. Now, if we look at this case, the first one, so we can tell that this is not possible, because in that case, it will not be a generalized linear phase system, right? Because the conditions are that the poles and zeros must be in complex in the conjugate reciprocal pairs, and that condition is not true in this case. So on the other hand, in this case, if we have something like this, because of the all pass system, we can have a reciprocal here, and this system is overall a generalized linear phase system. So that is why we can eliminate the possibility of case 1, and case 2 is the only possibility that we have. So what we can say is that if we want the overall system to be generalized linear phase system, then the minimum phase part, or the poles which are inside the unit circle, must be in a complex conjugate pair. Or we can say that the minimum phase system must have an order of at least 2. So that is what this says, that all the zeros and poles of h min z's must be of second order in order for that equation to be satisfied, that the overall system is a linear phase, generalized linear phase system. So uh, here it is written that when the all pass filter flips a pole or zero outside the unit circle, one is left in the conjugate reciprocal location, and that is why it gives us linear phase in this case, and that is why this is a only possibility. So uh, in the first part, we have determined that if this condition has to hold, then the minimum phase part must have its poles and zeros of the second order. And now let's look at the second part. In this case, we have been given a generalized linear phase FIR system. Its impulse response with real values is such that Hn is equal to 0 for n less than 0 and for n greater than equal to 8. So that means that Hn exists between 0 to 8. And this is the impulse function. Hn is equal to minus h7 minus n. And we have been given that the system function of this system has a 0 at this location and a 0 at z is equal to minus 2. And we have to determine the system function h of z. So a few pointers are that, first of all, clearly by looking at this, we can tell that it is a one of the FIR filters, and this impulse response is actually antisymmetric because there is a negative sign here. So that means that it is either a type 3 FIR system or a type 4 FIR system. And another thing to note is that m is equal to 7 in this case. So that means that m is odd. That means it's a type 4 FIR filter. So these two things we can simply determine by looking at this impulse response. So coming to the question, we have to find out h of z, given that these two are the zeros. Z is equal to 0.8 e raised to the power j pi by 4 and z is equal to minus 2. So this is the information that is given to us. So we compare it with the impulse response of the form Hn is equal to minus Hm minus n, which shows us that it is anti-symmetric, that is, it is type 3 or type 4 FIR linear phase system. And since m is odd, it is a type 4 FIR linear phase system. Now we consider the properties of type 4 filter. So the properties are that the zero occurs in conjugate reciprocal pairs. So that means that since it is given to us that z is in minus 2, obviously its conjugate is z is minus 2 only. So that is out of question. Another case is its reciprocal, which will be at z is equal to minus 1 by 2. So we have got from this one another location of 0. And we have also been given that z is equal to 0.8 e raised to the power j pi by 4 is one of the zeros. When we calculate its conjugate, it will be minus j pi by 4 in the power. We can also calculate its inverse, which is this one, 1.25 e j raised to the power j pi by 4. And then obviously the conjugate of this reciprocal, which will have the power of e as minus j pi by 4. So from this we have got 1 2 3 4 5 6 6 zeros we have obtained. And using again the property of the type 4 filter, we know that for a type 4 filter there must be a 0 at z is equal to 1. So we have got another position of 0, that is z is equal to 1. So we have got all the 7 zeros of this type 4 FIR linear phase system. We can now write h of z based on this. So it will be all these zeros at this position. This is at 1 by 2 uh, and this is at 2 2 1 by 2, and these four pairs, which is one complex conjugate pair and its reciprocal, and finally one at z is equal to 1. So this is the overall h of z, comprised of all the zeros of the system, and this is a type 4 FIR linear phase system. So on the basis of this system function, we were able to determine the zeros. And this was the last question. So this is the end. These were the questions for tutorial 10. Do you guys have any doubts?
No, sir.
Okay. So I guess if all questions are clear to everyone, then we can end this tutorial here. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.